All right, this is section 1.3, linear equations, day 2. So here are essential questions for today. So how can I write linear equations in two variables? So how do we actually write the equations that model relationships? Use slope to identify parallel and perpendicular lines. So looking at that special relationship when lines are either parallel or perpendicular. And then how can I use slope in linear equations to model and solve real life problems? Because again, as always, we're looking for how can we use what we know about mathematics to help explain our world, to look at problem solving and use those applications. So that's our plan for today. So before we get started, I want to see what you know already about parallel and perpendicular. So if you can just take a quick moment, pause the video, write down your thoughts about what you know about parallel and perpendicular lines. All right, well, hopefully you had a chance to talk a little bit about parallel and perpendicular, just kind of as our get ready for the lesson today. So parallel, some things that people often will say are that they are lines that don't cross, so they don't intersect. So we sometimes having a picture is the easiest way to be able to do that. If they don't intersect or cross, there's something that's the same about them, and this is a situation where the slopes are equal. So they have the same slope, they have the same rate of change. Perpendicular, those are two lines that meet in a very special way. So they do cross, but they meet at a right angle. So what do we know about their slopes if they meet at a right angle? Well, their slopes have to be opposite. So opposite sign. So if one's positive, the other's negative, they're going in opposite directions, and they are reciprocals of one another. So they are opposite reciprocals. So we're going to talk a lot more about that, but hopefully you have an idea in your head about what parallel and perpendicular mean for lines. So we'll use that in a little bit. All right, so let's talk about writing linear equations. We already know one form of a linear equation. Well, you know all of these already, but just to review, we've talked about slope-intercept already this year. So slope-intercept, y equals mx plus b, super user-friendly for graphing, right? We know a slope, we know an intercept, we can make a really easy, quick graph. Well, there's other versions, though, that can also be very useful. Point slope is one of those. It's a great way for writing the equation. So point slope form. Think about what it's called, point slope. That means you must need to know a point. So they're using this x1, y1, like an actual point on the line, and then the slope, so the rate of change. If you know a point and a slope, you're going to be able to write the equation very easily. So just knowing these two pieces of information, and hopefully you remember point slope from Algebra 2, but let's take a look at this again and see if this makes sense to you. So y minus y1. So y representing the y values of the equation minus this specific y value from the point that you know equals m, and then in parentheses x minus x1. What's interesting about point slope, if you just divide both sides of this equation by x minus x1, it is the slope formula. So point slope form is really just coming from the slope formula, which is kind of a nice way to think of it as well. So point slope form is most useful for finding the equation of a line. So if you're trying to write the equation, it's so handy, it's so easy to have those two pieces of information, because we don't always know the y-intercept, but we often know a point, a specific location. So finding the equation of a line. So if we're trying to write the equation, great way to do it, point slope form. If we're trying to graph, for sure, slope intercept. So it's a nice kind of a comparison. So if we're trying to graph or make a quick sketch, slope intercept form is a great way to go. So y equals mx plus b. So it kind of just depends on what you're going to do. Your textbook talks about a two-point form of the equation, which basically just means find the slope first and then put it into point slope form. It's kind of a crazy deal. We're not going to talk about that. We don't really need it. So we're gonna skip over that. We're gonna get right to an example. So we're gonna take a look at a checkpoint. So this is an additional example. Notice again, has the video link in the book as well. So it says find the slope intercept form. So important. We know what form they want, of the equation of a line that has the given slope and passes through the given point. Now we're going to do scenarios like this that aren't really like real life application, but we have to think about what is the process that we use so then we can actually apply it in a real situation. So looking at a real scenario, if we can figure out the slope and we know a specific value, then we can use the same process. So we're going to practice the process a little bit. So think about what you know. You're given a point and you're given a slope. So what seems natural then is I would probably want to use point slope form because that's what I know. Ultimately, they want slope intercept, but I can get to that form after I have point slope. So it's pretty quick, but there are different ways to do it. So we're going to go from the point slope perspective first. So think about what point slope form says: y minus y1, m times x minus x1. I can actually put in those values. My x1, y1 are the actual ordered pair values from the point that I know. So y minus a -7 equals m, that's the slope, so that's the 2, and then x minus 3. Be super careful that you're putting the x's with x's, y's with y's. Be careful on your signs. And if all they said was, hey, can you give me an equation of a line? You could stop there with the green one. Like that is an equation of a line. I maybe would clean this up. Y plus 7 minus a negative, but that's an equation of the line. Problem is, it's not very user-friendly. You can put it in your graphing calculator, and ultimately, it's not in the form that they're asking us for. So what's the difference between point slope and slope intercept? I'm going to go back to the equations here. Slope intercept is solved for y. So all we have to do to get from point slope to slope intercept is solve for y. So when we think about like what's the relationship here, let's just get the y by itself. Then we'd be able to put it in our graphing calculator. Everything would be great. So what two things would I need to do to solve it for y? Well, I'm going to have to move the plus 7 for sure. But I also think I'm going to need to distribute here so I can put like terms together. So 2x minus 6. And then I'm going to subtract that 7. So just be careful on your arithmetic. So y equals 2x minus 13. So this has a slope of 2. Well, right, we knew that. And it actually has a b value, or y-intercept, of -13. So if I wanted to graph, I could have graphed it from the original or from this. So here is my slope-intercept version. Now let's talk about the relationship between these. It's just solving for y, right? That's all we had to do. We distributed to get those terms separate, and then we moved the 7 over. That's one option, and it works really well. Some of you might have been thinking, oh, I think I would maybe do this a different way. What if I just want to go straight to slope-intercept form? So could I do that as well? Well, sure you can, because you know a slope. So let's see if we can think about it from this perspective. I know a slope. But the problem is, then I still need the b value, right? I don't know b. So here's what you'd have to do. You're going to do the same kind of idea. I'm going to use the values that I know, and I'm going to substitute those in. So I'm going to put the 3 in for the x, and I'm going to put the 7 in for the y, that particular point, and then I can solve for b. So I'm going to put in the -7 for the y, the actual specific number, and then the 3 for the x, and then I'm going to go ahead and solve for this b value. So that would be 6 plus b equals -7, subtract 6, and I get b equals -13, and then I still have to go back and actually write the slope-intercept equation then. So y equals, my slope was 2, and my y-intercept -13. Same exact thing. Doesn't really matter, right? It's about the same amount of work. Some people have really strong preferences one way or the other, but we have options, right? So it just depends on what is the easiest method for you. Let's take a look at another example. It says find the equation of a line that passes through these 2 points. So it's going through 2 points. And you want to do it in point slope form, and you want slope intercept. So we actually do want the point slope form for this one, and then slope intercept. So we want both. All right, so I'm giving you different information. The last one I gave you a point and a slope. Cool, plug it in, right? Point and a slope. Now I'm giving you 2 points. In either of these formats, notice they both have the word slope in them. So I'm going to have to be able to find what the slope is. So regardless, I'm kind of short a little information here. I got plenty of points. What could I do? So think about that. Maybe pause the video for a sec if you need to. How can I solve and write an equation if I'm given 2 points? What would you need to do first? All right, well, hopefully you're thinking about, gosh, I need to know the slope. So is there a way to find slope if you know 2 points? Well, yeah, we have a slope formula. Some people might graph it and count on the graph, and that's fine if you have numbers that work well. I would just use the formula. So remember what our slope formula is: y2 minus y1 over x2 minus x1, rise over run, right? We've talked about that. So it doesn't matter which point you pick, just be consistent. I think I'll do 7 minus 5, and on the bottom would have to be -3 minus 1. Remember, it's really easy to mix up your numbers. So some way that you can highlight for yourself, oh, those are my y's, these are my x's, just be really careful. Okay, take a second, go ahead and calculate your slope. Pause the video if you need to. And be careful, make sure you simplify. So it looks like we have a slope of -1/2. So it looks like we're going to have -1/2 for our slope value. So this is a decreasing, falling to the left, to the right as we see this graph. All right, so we have a slope now. Awesome. So how would we find, let's do this first part here. How would we find an equation in point slope form? Well, you need a point and a slope. Well, I have a slope, and I actually have 2 points. So does it matter which point you use? So that's my first question. I have 2 ordered pairs. Does it matter which one I use? Well, they're both on the line. So the answer to that question is no, it doesn't matter. So I'm going to do it both ways. We're going to do it using the 0.15, and then I'm also going to use it using the point -3.7, and we're going to compare and see what we notice. So we're going to do it both ways. So let's go ahead and do point slope form. So y minus y1 equals m, which is our -1/2, and then x minus x1. So that's using the first point. And then we're going to do the same thing, y minus y1, which is the 7, our slope -1/2, x minus a -3. Now, right away, if you want to minus a -3, you could go ahead and just say plus. All right, now let's take a peek. There's 2 different versions of point slope form for this linear equation that we have. What if you knew a different point on the line? Could you also write that one in point slope form? Sure. These equations don't look exactly the same. Well, of course not, because they're different points. They have the same slope, though. So how many points or point slope forms of an equation of a line could you write? Well, infinitely many, because there's infinitely many points on a line. So point slope form, there's all sorts of different ways that you can write the equations that are all true for that particular line, because there's infinitely many points. So what would be the advantage then to writing this equation in slope-intercept form? So y equals mx plus b, slope-intercept. Well, in slope-intercept form, how many different versions of the line are you going to have? Only one, right? There's only one way that you can do this because there's only one slope for this line and one intercept. So the advantage to slope-intercept form for a lot of people is that there's only one equation that I have to think about and recognize for a particular line, where point slope, there's infinitely many that I have to choose from. So it just kind of perspective. It is really nice. Oops, infinitely many, if I can spell correctly there. There's so many different ways that you can write it. So some people, they like that because it's easy. They can pick any point. But then slope-intercept form, there's just that one way to do it. So how do we get, again, from point slope if I want to change over into slope-intercept? Well, you solve for y. That's one way to do it. So you could pick either of these two. It doesn't matter. So I'm going to kind of walk through it in both. We could pick either of these, oops, and we can solve for y. So go ahead and pause the video. Do your solving for y. See what you come up with. All right, so what we want to check now is see, did we get the same thing? So I solved for y in both of these, and I got the exact same thing. So my point slope form, no matter what point I start with, when I solve for y, I ended up with the same thing. And you could write it 5.5 or 11.5. Just be careful on your arithmetic there. So y equals -1/2 x. Oops, forgot my x there. And then plus 5.5, however you want to write that. So moral to the story, if you're given 2 points, we need to find a slope. So we did that first. And then we can find infinitely many point slope versions that are all going to represent this particular line, but there's only going to be one slope-intercept version because there's only one y-intercept for each line, one place where it crosses the y-axis and that unique slope. All right, so let's talk about and take that forward into parallel and perpendicular now. So when we talk about this, we already did our little introduction for this. In a relationship where 2 lines are parallel, what do we know about that? Well, their slopes are equal. So they have the same rate of change. They don't cross. So the slopes are equal. The relationship between lines that are perpendicular, the slopes are opposite. That means one's positive and one's negative, and they are also reciprocals. So let's make sure you remember what reciprocals are. If you have the number, say 1/3, the reciprocal would be 3/1. And if we're actually going to make this perpendicular, if that one was positive, this one would have to be negative. So remember what that means to be opposite reciprocal. So for example, it says a line that is parallel to a line whose slope is 2. Go ahead and fill that in. What do you think it would be? What would be the slope of the line parallel to a line that has a slope of 2? Well, it would have to have the exact same slope, right? So same rate of change. What about a line that's perpendicular to a line that has a slope of 2? So opposite reciprocal of 2. So go ahead, pause the video for a sec, jot down what you think your answer should be. So if the original slope is 2, Opposite means it's going to be negative, and reciprocal would be 1 over 2. So remember, make any fraction or any number a fraction, just put it over 1 so you have something to flip. So it would be negative 1/2. Something else to note, when you multiply together two slopes that are perpendicular, you should always get -1. Opposite reciprocals will multiply to -1. It's a good other check if you're not certain if two things are perpendicular. All right, so let's take a look. We're going to practice our equation writing here. So we're going to find the slope-intercept form. So we have an additional example here of equations of a line that goes through this point. So this is the point, the x1, y1. We have a location. And we're going to do parallel to first, and then perpendicular to this line. All right, so we've talked about lots of different things. I can just tell you a slope and a point, right? That was pretty easy, and we can write the equation. I can give you 2 points, and you can write the equation because you have to find the slope first, and then you've got a point already. This is, yet again, another scenario. So I'm giving you a point. We always seem to have a point. We know a location, but we need slope. If we know it's parallel or perpendicular, that has to do with slope. So somehow from this information, we need to figure out slope, right? So let's take a look at this last part. If you know it's parallel or perpendicular to another line, and we know what the relationships are there for slopes, what if I just find the slope of this line? What if I knew that? So is there a way I can find the slope from that equation? Well, this is in what we call standard form, the ax plus by equals c. It's standard, right? We can write every line that way. It's not necessarily as user-friendly, though, for being able to recognize it. What would be a better form to be able to recognize the slope? So what could we solve for? Well, how about we solve for y and get it into slope-intercept form? Then we'd be able to tell the slope really easily. So that's the first thing I'd like you to do. Go ahead and solve this equation for y. So go ahead and pause the video and go ahead and solve. All right, so solving for y, a couple things to note. When you subtract the 5x on each side, I like to write it first then, because then I get that y equals mx plus b going, so it's a little bit easier to recognize. Be careful that you divide by a -3, so when you do a negative divided by a negative, it's a positive. So let's take a look at this slope-intercept equation. Can you identify for me what the slope is of that line? So which one is the slope? Well, it's always the coefficient, the number part of the x term. So our slope is 5/3. So now I know the slope of the line that my line has a relationship with. Okay, so let's take a look at the first relationship we're supposed to look at. What if the line is parallel to this one over here? Well, if it's parallel, that means it's not going to intersect. It has the same slope. So that means my slope would have to be 5/3. And it's going to go through this point -4, 1. So I have all the information I need. I have a point and I have a slope. So for a lot of people, then they're going to fall back to this point slope form first, because it's a really quick and easy way to write the equation. And then to get it into slope intercept, they can just solve for y. So let's go ahead and put those in. I'm going to give you a second, have you pause the video so we can solve for y. So we have y minus, okay, which one's the y value? Just be careful in your ordered pair. Make sure you grab the right number. So y minus 1, and then our slope was 5/3, and then we have x minus a -4. Okay, so here's what I'd like you to do. This is point slope form. If they just said, hey, write the equation of a line, you'd be done. But they said slope intercept because it's more user friendly. We can put it in the graphing calculator. There's only one of them for every line. They want you to solve for y. Pause the video, solve for y. All right, so let's take a look and see how your arithmetic went. So the first thing we do is we distribute. I also did minus a negative as plus positive. So distribute. I left it as a fraction. You could write it as a mixed number if you want. Just be careful, it's not an exact decimal, so don't do decimal. Add the 1, we get 23/3 or 7 2/3. So this is the line that is parallel to the line that we had. All right, so let's take a look at what the second relationship is that they want us to do. They want us to do perpendicular. All right, so if the line that we want is perpendicular to this one, that means the slopes have to be opposite reciprocals. So if my original slope was 5/3, go ahead and write down what the opposite reciprocal would be. So opposite, this one was positive, so I want negative, and the reciprocal of 5/3 would be 3/5. So again, I have a point and I have a slope. I'm going to be able to write that equation. So my point was -4, 1. But now my slope, if it's perpendicular, is -3/5. So we're going to go ahead and use our point slope form again. It's just a little bit easier for me anyway. And then we're going to do the same thing. Again, we could write infinitely many of these depending on what point we know. Let's get into slope intercept form so we can talk about it. So go ahead and pause and solve for y. Alrighty, so we solve for y. So again, distribute, add the 1, and now we have y equals -3/5. You could say -7/5 or -1 and 2/5. This one does have an exact decimal equivalent, so if you wanted to write it as a decimal, -1.4, that would be fine as well because it's an exact. All right, so just be careful about the relationship between what your line is and the line that you're trying to write an equation with. So make sure you know how to find the slope. So that's really the biggest thing. So if you're given 2 points, we have a formula. We can calculate the slope. If you're given an equation and a relationship, we need to figure out the slope of that other equation, which we did by solving for y up here. So that's our idea. All right, let's talk a little bit more about slope then to finish up for today. So our last few things are going to have to do with applications of slope. What's really interesting is people sort of use these words interchangeably, but in real life problems, a slope actually can be represented in 2 different ways. It can either be written as a ratio, or it can be written as a rate. And I think people use the words rate and ratio, again, interchangeably, but they are a little bit different. So if the x and y axis have the same unit of measure, so like inches to inches, feet to feet, miles to miles. When you reduce that fraction, the units divide out. It has no units left, and that's considered to be a ratio of things. If the x and y axis have different units of measure, so x and y axis have different units of measure, then the slope is considered a rate, or that's kind of a shortened version for a rate of change. So it's a rate, and we use rates all the time. We use ratios all the time, actually. So we just have to know kind of the difference between what those are. So same units of measure, ratio, different units of measure, it's a rate. So we can talk about a whole bunch of real life examples, but let's talk about rate of change first, because I feel like that's going to be a little bit easier for people. So think about something that when you drive. Is there a rate of change that you can think of when you drive? Well, how about the speed limit? So if you think about speed limits, that's in miles per hour. Notice the units are different, miles and hours. So if you're going to write it as a fraction, it would be miles over hours. That's a great example of a rate of change. You could talk about, how about if you have a part-time job, you get paid, right? What do you get paid? Whatever that is, that's called your hourly, usually, wage. So you get paid per hour. So your hourly wage, so it would be dollars per hour. Hopefully it's a lot, right? So dollars per hour, that's a rate because those units are different and they can't be made the same. They are completely different. Gas mileage, how many miles per gallon do you get? That's a rate. All right, let's talk about some ratios. So ratios sometimes are harder for people to think about. If you've ever driven out in the mountains anywhere, they talk about the grade of a road usually. It has to do with the steepness, how steep a road is. If you talk about skiing and ski hills, the black diamonds, all that, they talk about how steep something is, and that's usually where the units are the same. So it's the change in the vertical over the change in the horizontal, which is what a slope is, right? So the steepness of whatever. So you could have the change in the vertical. So how much does it go vertically? Usually measured in whatever units that makes sense. So how many feet does it go up and down? For how many feet does it go over? So like change in vertical over change in horizontal, exactly the slope, but those units they're going to be exactly the same. So it might be how many feet per how many feet. So I went up 7 feet for every 1 foot that I went over. That'd be pretty steep. As long as the units can be made the same, that's considered to be a ratio. So we want to take a look at a few examples that illustrate that, so we can work with that a little bit. All right, so let's take a look at this one. You might have to kind of pause to jot down information or just kind of read it through. We're going to take a look at a wheelchair ramp. So it's American Disabilities Act requires that every public building, have access for people with disabilities. So this is a pretty common thing, and we see them all over the place, but you don't want them too steep, obviously. And they take up a lot of room. It can be hard to kind of fit that in if they're too flat as well, because it would be a long ramp and kind of difficult for people to use. So you want it kind of in an appropriate range of steepness. So what they're saying is the recommended slope of a wheelchair ramp is 1 to 12. Okay, so what that means is it's a ratio because those units are the same. 1 to 12, they're talking about, so you notice there's no units with that, so the units have divided out. So that means for like every 1 foot it goes up, it's going over 12. Up 1, over 12. So that's the rate of that. Sometimes it's nice to actually kind of draw this out so you can think about what that means. So if this is our ramp, that means for every 1 foot it goes up, it's going over 12. Or for every 1 inch it goes up, it's going over 12 inches, however you want to think about that. So a business is going to install a wheelchair ramp that rises 22 inches over a length of 24 feet. Is the ramp steeper than the recommended? So this is the recommendation. So this is what we're recommending. Is it okay? Is it too steep or is it within those recommendations? All right, I want you to go ahead and pause the video and see if you can come up with a solution for this. See if we can solve this one. All right, well, I decided to draw a picture because for me, it's nice to see things as a picture. So our ramp is supposed to rise 22 inches. So here's our ramp over 24 feet. Now remember, ratios are supposed to be the same unit. So this ratio was 1 whatever to 12 whatever. They didn't tell us. It could be any units. What we have right now, 22 inches in the vertical change over 24 feet. So right now our units are not the same, but can we make them the same? Then it would be a ratio. So how would we make them the same? Well, you either can change inches to feet or feet to inches. What do you think's easier? How many inches in a foot? 12, right? So for me, it's probably easier to convert my feet to inches. So I'm going to multiply by 12 inches per foot. So the feet would cancel, and I'll be left with 22 inches over, okay, 24 times 12, 288 inches. Notice what happens here. The units cancel. So 22 over 288. So my question is that too steep or are we okay? So how are you going to compare these two fractions? What might be the easiest way to do that? Well, a lot of people, what they do is they take a look at what the decimal equivalent is. So this is about 0.076, which would be like a 7.6% grade or steepness. The 1 divided by 12 is 0.083, so 8.3%. So our number is less. We're within the recommendations of the 88. So that's a great way to be able to tell that. So there are reasons that people have to actually make these calculations, but that's what a ratio would be, where the units can be made the same. All right, let's take a look at the next one here. I want you to think about what the information is telling you in this one. So we're going to look at some other applications. So we're going to take a peek at a few examples. So it says an accounting firm determines that the value in dollars of a copier T years after its purchase is given by this. Interpret the slope and the y-intercept. In real life situations, one of the things we have to be able to do is determine what the numbers represent. What does it mean? It's not a very useful model if we don't understand what the numbers mean. When you buy things, the value starts going down right away. It's called depreciation. Depreciating, it's going down. If something appreciates, that means it goes up. So we have a bigger value. Some collectibles do that. The value gets higher. But for a lot of things we buy, cars, photocopiers for sure, we have to replace them all the time. But it goes down each year. So the value gets smaller and smaller. So I want you to think about what this model might tell you. So what does the slope number represent and what would the y-intercept? So if you think about graphing this, so my x value is actually t, so it's time. So we have the time axis. And then actually our y is v, the value in dollars that the copier is worth. Okay, so can you tell me what the slope is? So which number represents the slope? Well, it's negative 300, and then the b is 1,500. So this is starting at $1,500. And what is it doing? It's going down $300 each year. Okay, so not exactly to scale, but just to get the idea. The value of the copier is decreasing, of course, because it gets old. So what do these numbers mean? So this is at time equals 0. So when t is 0, the value of the copier was $1,500. So when they first purchased the copier, the value was $1,500. So the value of the copier, so we'll say the value of the copier when purchased, so when they first got it, time equals 0, is $1,500. And what's going to happen is it's going to go down $300 every year after that. So after a year, it'll be worth $1,200. After another year, it'll be worth $900, and it continues going down. So what does the negative 300 represent? Well, that slope means it's losing $300 per year. And what's losing 300? The value of the copier. The value of the copier decreases, because it's a minus, right? Decreases $300 per year. What's really important is for you to be specific, to not just say things like it or whatever. So we can be very precise. So the value of the copier is actually decreasing. That's what this model is doing. So we could figure out then, after how many years would the value be 0? Where would that be on the graph when the value is 0? Well, right here when it hits v equals 0. So when would the value be 0? So when would that happen? After how many years? We could figure out what that would look like and be able to do that model. So let's talk about this idea of straight line depreciation. So basically what that means is what we just had. It depreciates or goes down the same amount each year. So the value goes down the same amount each year. So the value decreases the same amount per unit of time. So I'll just say per unit of time, because it doesn't have to be per year either. Things could be depreciating faster or slower than that per unit of time. So straight line means there's a constant slope. So linear or straight line, you're talking about a constant slope then. So let's take a look at what we just did. We did one that was already written. This is one that I want you to see if you can write the value for. So go ahead and kind of read through this here. A manufacturing firm purchases a machine that's worth this much money. So when they first purchased it, that's what it was. The machine had a use life of 6 years. So they knew that it would last for 6 years, but after 6 years, it would have to be replaced because it wouldn't have any salvage value anymore. Write a linear equation that describes the value of the machine each year. All right, well, this is a super similar scenario to what we have. So we're trying to write an equation for values. So you might want to use V to represent the value of the machine each year. So the value of the machine. You can use whatever variable you want, but sometimes it's helpful to know and use a letter that makes sense, helps you remember what you're talking about. We're talking about it changes value dependent on what? What is our independent variable that's changing that causes this to go down? Well, it's after how old it is. So it's time. So we're talking about time. So the t equals time in years is going to be our independent variable here. What changes that causes the value to go down? All right, can you tell me what the value was initially? Well, that was the 24,750. That means it's its y-intercept. At time equals 0, the value of this was 24,750. That's your y-intercept or your b value. So we know what our b value is in the equation. It's 24,750. Let's see if we can figure out our slope. Our rate of change. How much is it going down each year? So what they gave us is they said, hey, after 6 years, it would have no salvage value at all. So we can figure out from that what this slope is. So we can figure out what that rate of change is and be able to solve. So initially, we had at time 0, it was worth 24,750. After 6 years, it's worth nothing. So can we figure out a slope for that to be able to solve? So you can think of them as ordered pairs and go ahead and subtract, but we'd have 24,750 minus 0, right? So going through our y's, and then our x's, I'd have to start with the 0 minus the 6, and it looks like 24,750 divided by 6, I think that's 4,125. But notice we've got a positive divided by a negative. So it's depreciating at $4,125 per year. So the value is decreasing. So this is a rate per year, right? So when we think about dollars per year, how much is it going down? So when we know what it starts at and what the value starts at and when it's going to be worth nothing, we can calculate the slope for that. So now we can write our model. So our value is going to be depreciating at $4,125 per year. And it's starting at a value of 24,750. So now could you project, you could graph this on your graphing calculator, you could project the value of the copier at any given year, and we'd have a really good idea of what's happening. So that's our kind of our goal in real life settings, is to be able to do something like this. Take the data that we know and be able to write a model for it. All right, so now we're going to take a look at sales. A lot of money examples because there's a lot of real life examples revolving around money. So let's take a look and see if we can get an idea of what could be happening in this situation. So these are actual sales for Foot Locker, 6.5 billion in 2013 and 7.2 billion in 2014. Could you use that to predict the sales in 2017? So how could we do that? So think about, first of all, if you're going to try to predict the sales, we have to assume something. We have to assume that it's going to continue, in this case, growing, right? Because the number went up at the same rate of change. So just like we had straight line depreciation, we're going to assume straight line or linear appreciation, that the values are going to go up at the same rate. So we have to be careful on that. Could we figure out how much the sales are changing now to help us figure out what to do in 2017? So let's think of these as we would graph them. So if we thought about it as a graph, we'd have time and sales. So my Y value is the sales, my time is the X variable. So I could think of these as ordered pairs. So in 2013, it was 6.5 billion. And then in 2014, it was 7.2 billion. So couldn't I figure out the rate of change there? So let's see what that slope looks like. So I would have my change in Y. So 7.2 minus 6.5 over change in X, so 2014 minus 2013. So per 1 year, so this was a 1 year change. It looks like it was 0.7. Okay, so what does 0.7 mean? That means the sales increased, because it's positive, right? 0.7 what? Billion dollars per year. That'd be awesome, wouldn't it? So it's going up almost $1 billion per year. All right, so how could I use that to project then? So I know what it's doing now. I have what the pattern is. How would you project 2017 then? What can I do to project 2017? Well, I'm going to have to figure out an equation that would model that. So I would want to figure out what would that be, and then I can actually put that in there. So if I have the equation that models the situation in general, then I can put in a value for 2017 to be able to do that. So some people might just start adding on. We know where it was in 2014, so I could add 0.7 to get to 2015. I could add 0.7 again to get to 2016. I could add 0.7 again to get to 2017. Works great. If that's all you want to do is that 1 year. But what if you want to continue to project out past that? An equation would be a great way to model that. So it might be a little bit easier way to do that. So we're going to go ahead and see if we can write the equation that models it. So I think we know some points. We also know a slope. I'm going to go ahead and use point slope form. And remember, point slope form, you can use whichever point you want. So you can decide. I'm going to go ahead and use the first one. So 2013, 6.5. There's my point, and my slope is 0.7. So can you go ahead, pause the video, write it in point slope form. All right, so we're going to go ahead and distribute this through and solve for y, so we have a little bit easier model to deal with. So 0.7x minus, looks like, go ahead and multiply that out, 1409.1, and then y minus 6.5. Then go ahead and add the 6.5, and we'll have our model here. So y equals, we could have done S, I guess, S for sales, T for time, whatever variables make the most sense for you. 0.7x minus looks like 1402.6. So here's the model that we can use to predict the future. So if you would prefer, if you wanted S for sales and T for time, or Y in years, whatever you like. So what do we want to use? We want 2017. So that means our X value is 2017. So we're going to replace this X with 2017 and then go ahead and solve. So go ahead and calculate that. So pause if you need to and type that on in. And it looks like we're going to come up with 9.3. All right, so what does 9.3 mean? That means 9.3 billion. Remember, it's not just $9.30. $9.3 billion of sales for Foot Locker in 2017. Remember to be super specific. So where were these sales? What are the units? How much? When did that occur? So we could use that model. But now you could also figure out 2020, and you could do 2025, and you can figure out whatever year you want to by using a model, having an equation. So it's really powerful. All right, we've talked about a lot. This is a big day. We had a lot of different things that we're dealing with. So being able to write equations and having those relationships, being able to go back and do slope and parallel and perpendicular. So this was a really big day talking about how to write these equations.